The universe is a place of staggering scale and infinite mystery, home to over 100 billion galaxies, each teeming with billions of stars. Yet, even among this vast expanse, there are phenomena so extraordinary, so utterly beyond our everyday understanding, that they seem to defy the very laws of nature. Today, we're diving into 22 hidden wonders of the cosmos, each one a breathtaking enigma that will challenge what you thought you knew about the universe. From celestial bodies that warp time and space to cosmic events that stretch the limits of imagination, these marvels will leave you spellbound. And it all begins with a cosmic mystery so profound, it redefines the way we see the fabric of existence itself. Ready to explore the unknown, let's begin. Hidden deep within the cosmos lies a force so powerful, it's pulling entire galaxies toward it, a phenomenon so mysterious it's known as the Great Attractor. Imagine a cosmic magnet, invisible yet irresistible, tugging at everything in its vicinity, including our own Milky Way. But here's the twist: this gravitational anomaly sits in a region called the Zone of Avoidance, an area obscured by the thick dust and stars of our galaxy's plane. It's like trying to solve a puzzle while someone's holding a curtain in front of it. For decades, scientists struggled to study this enigmatic force, but thanks to advanced telescopes like the Hubble and radio observatories, we're slowly peeling back the layers of this cosmic secret. What we've discovered is astonishing. The Great Attractor isn't just a single object but a massive concentration of matter, reshaping our understanding of the universe's large-scale structure. It's a reminder that even in the vastness of space, there are forces at work that bind everything together in ways we're only beginning to comprehend. And just when you think the cosmos couldn't get any more mysterious, another gravitational wonder awaits, one that bends the very fabric of reality itself. Picture a galaxy, a swirling, glittering tapestry of stars, gas, and dust. Now imagine that everything you see is only a fraction of the story. What holds these immense structures together isn't just the gravity of the stars and planets we can observe. No, there's something far more elusive at work: dark matter. This mysterious substance doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet its gravitational pull is so immense that it acts like an invisible scaffold, holding galaxies together and shaping the very fabric of the cosmos. Think of it as an unseen hand guiding the delicate dance of stars, planets, and cosmic dust across the universe. Without dark matter, galaxies would simply fly apart. Its gravitational influence is so powerful that it bends the paths of light itself, a phenomenon known as gravitational lensing. This effect allows scientists to map the presence of dark matter, even though we can't see it directly. It's like trying to find a ghost by watching its footprints in the snow. But what exactly is dark matter? That's the question physicists have been racing to answer for decades. Experiments deep underground, like those using liquid xenon or ultra-sensitive detectors, are hunting for elusive dark matter particles, hoping to catch a glimpse of this cosmic enigma. The implications are staggering. Discovering dark matter could revolutionize our understanding of physics, revealing new dimensions of reality we've yet to imagine. And just when you think the cosmos couldn't get any more mysterious, consider this: dark matter isn't the only invisible force at play. Beyond its shadowy influence lies another phenomenon that challenges our very perception of light and energy, a cosmic mystery so profound, it's reshaping how we understand the universe. But that's a story for the next wonder. Now, let's turn our attention to one of the most dazzling and enigmatic phenomena in the cosmos: quasars. Picture a cosmic beacon so bright, it outshines entire galaxies, its light traveling billions of years to reach us. These luminous giants are powered by supermassive black holes lurking at the centers of distant galaxies. But these aren't your typical black holes quietly consuming matter in the shadows. No, quasars are the result of these black holes feasting on gas, dust, and stars at an almost unimaginable rate. As material spirals inward, it heats up to incredible temperatures, releasing torrents of energy that make quasars some of the brightest objects in the universe. What's truly mind-boggling is that quasars can emit thousands of times more energy than the entire Milky Way, all from a region no larger than our solar system. They're like cosmic lighthouses, their beams cutting through the darkness of space and time, allowing us to peer back into the early universe. In fact, the light from the most distant quasars began its journey when the cosmos was just a fraction of its current age. By studying this ancient light, astronomers can learn about the conditions of the primordial universe, from the formation of the first galaxies to the reionization of space itself. But quasars aren't just windows to the past, they're also key to understanding the evolution of galaxies. The supermassive black holes at their cores play a crucial role in shaping their host galaxies, influencing star formation and the distribution of matter. It's a cosmic feedback loop where the black hole's appetite and the galaxy's growth are intricately linked. And yet, for all we've learned, quasars remain shrouded in mystery. How do they form? What triggers their incredible outbursts of energy? And what happens when they finally exhaust their fuel? As we continue to unravel these questions, quasars remind us that the universe is a place of both beauty and chaos, where even the most extreme environments hold clues to the grand story of existence. And speaking of extremes, our next wonder takes us to a celestial object so bizarre, it seems to defy the very laws of physics. But that's a discovery for the next chapter in our cosmic journey. Among the most extreme objects in the universe are neutron stars, cosmic remnants so dense they defy comprehension. Born from the explosive death throes of massive stars, these stellar corpses pack the mass of a sun into a sphere no larger than a city. To put that into perspective, imagine compressing Mount Everest into a sugar cube. A single teaspoon of neutron star material would weigh billions of tons, a staggering density that challenges our understanding of matter itself. But density is just the beginning of their story. Neutron stars are also home to some of the strongest magnetic fields in the cosmos, trillions of times more powerful than Earth. These fields, combined with their rapid rotation, give rise to one of the most fascinating phenomena in the universe, pulsars. Picture a lighthouse beam slicing through the darkness of space, but instead of light, it's a rhythmic pulse of radiation sweeping across the cosmos. When astronomers first detected these pulses in 1967, they were baffled. The regularity was so precise that some even speculated it might be a signal from an alien civilization. They jokingly dubbed the signal LGM-1, short for Little Green Men. Of course, the truth was even more extraordinary. The pulses weren't messages from extraterrestrials, but the natural emissions of a rapidly spinning neutron star. This discovery opened a new window into the universe, revealing the extreme conditions that exist in the aftermath of a supernova. Pulsars have since become cosmic clocks, their precise pulses helping scientists test the laws of physics, study the fabric of space-time, and even detect gravitational waves. But neutron stars aren't just fascinating for their bizarre properties, they're also laboratories for understanding the fundamental forces of nature. At their cores, matter is compressed to such extremes that protons and electrons merge, forming a sea of neutrons. This strange state of matter, known as neutronium, is unlike anything we can recreate on Earth. Studying neutron stars gives us a glimpse into the behavior of matter under conditions so extreme, they push the boundaries of what we thought was possible. And yet, even these ultra-dense objects can be outshone by their more extreme cousins. When neutron stars collide, they unleash a cataclysm so violent it ripples through the fabric of space-time itself. These collisions are so powerful, they create gravitational waves, ripples in the cosmic fabric predicted by Einstein over a century ago. But that's a story for another wonder, one that takes us even closer to the edge of what we know about the universe. For now, neutron stars stand as a testament to the universe's ability to create the unimaginable, reminding us that even in the cold void of space, there's a world of extremes waiting to be explored. Now, let's venture into the heart of one of the universe's most captivating mysteries, black holes. These cosmic enigmas are regions where gravity becomes so overwhelming that nothing, not even light, can escape their pull. Imagine a place where the rules of physics as we know them break down, where time and space twist into something unrecognizable. At the edge of every black hole lies the event horizon, a boundary beyond which no information or matter can return. It's the point of no return, a one-way ticket into the unknown. But what lies beyond the event horizon, at the very center of a black hole, is the singularity, a point where matter is compressed to infinite density, and the laws of physics as we understand them cease to apply. It's a place where our current knowledge hits a wall, a cosmic riddle that challenges even the brightest minds in science. For decades, black holes existed only in theory and mathematical equations, their true nature hidden from our view. That is, until April 10, 2019, when humanity witnessed a monumental breakthrough. For the first time, the Event Horizon Telescope collaboration unveiled an image of a black hole, a glowing ring of light surrounding a dark void. This historic achievement, capturing the supermassive black hole at the center of the galaxy M87, was a triumph of human ingenuity and collaboration. The image confirmed Einstein's predictions about the bending of light around these gravitational giants, offering a glimpse into the invisible. It was a moment that bridged the gap between theory and reality, showing us that even the most elusive cosmic phenomena can be brought into focus. Yet, black holes are more than just cosmic vacuum cleaners. They play a crucial role in shaping the universe, influencing the formation of galaxies and the flow of matter across vast distances. Their immense gravity can warp space-time, creating effects so extreme that they alter the very fabric of reality. And while we've made incredible strides in understanding them, black holes still hold many secrets. For instance, what happens to the information that falls into a black hole? Does it vanish forever, or is there some way it's preserved? These questions push the boundaries of physics, challenging us to rethink our understanding of the universe. As we ponder these mysteries, consider this: black holes don't just challenge our knowledge of space, they also warp our perception of time. Near a black hole, time slows down dramatically, a phenomenon known as time dilation. It's a concept so strange it feels like science fiction, but this isn't just a theoretical idea, it's a real effect predicted by Einstein's theory of relativity. And as we explore the implications of time dilation, we're led to another cosmic wonder, one that stretches our understanding of time itself in ways we're only beginning to grasp. Imagine standing at the edge of a black hole, peering into the abyss. What you might not realize is that every second you spend there feels like an eternity to someone watching from afar. This isn't science fiction, it's one of the most fascinating predictions of Einstein's theory of relativity, time dilation. Near a black hole, the gravitational pull is so intense that it warps not just space but time itself. To understand this, picture an astronaut falling toward a black hole. For them, time ticks by normally, but for an observer far away, their movements would appear to slow down dramatically, almost as if they were moving in slow motion. It's a mind-bending effect that challenges our everyday experience of time as a constant, unchanging force. This phenomenon isn't just theoretical, it's been observed in action. For example, the Global Positioning System, or GPS, relies on satellites that orbit Earth at high speeds. Because of their velocity and the weaker gravity in space, time on these satellites actually passes slightly faster than it does on the ground. Engineers have to account for this tiny time difference to keep GPS accurate, but near a black hole, the effect is far more extreme. If you could hover just outside the event horizon, time would slow so much that years could pass for the rest of the universe while you experience mere seconds. It's like stepping into a cosmic time machine where the rules of time as we know them no longer apply. What does this mean for the future of space travel? If humanity ever ventures close to a black hole, time dilation could have profound implications. Imagine a crew embarking on a mission near one of these gravitational giants. While they might experience a journey lasting only a few years, centuries could pass on Earth. It's a scenario that raises both tantalizing possibilities and ethical questions. Could we use black holes as gateways to the distant future? Or would the risks like the crushing tidal forces that would tear apart any spacecraft make such a journey impossible? These questions push the boundaries of our imagination, forcing us to rethink what's achievable in the cosmos. But time dilation isn't just a tool for theoretical exploration, it also reshapes our understanding of reality. If time can stretch and bend depending on gravity and speed, then our perception of time as a fixed linear progression might be far too simplistic. Instead, time is fluid, a dimension as malleable as the fabric of space itself. This insight has profound implications not just for physics but for philosophy, challenging us to consider whether time is truly as universal as we once thought. As we grapple with these mind-bending ideas, another mystery awaits, one that ties the fabric of space and time even closer together. Beyond the warped reality of black holes, there are celestial objects that send out signals so strange they seem to defy explanation. But that's a story for the next wonder in our cosmic journey. Among the most perplexing signals in the cosmos are fast radio bursts, or FRB brief, intense flashes of radio waves that last just milliseconds but pack the energy of hundreds of millions of suns. These mysterious bursts were first detected in 2007, and since then, astronomers have been racing to uncover their origins. What makes FRBs so fascinating is their sheer unpredictability. They appear out of nowhere, often from galaxies billions of light years away, and vanish almost as quickly as they arrive. It's like trying to catch a firefly in a pitch-black room. Blink and you might miss it. Theories about what causes FRBs range from the extraordinary to the downright speculative. Some scientists believe they're the result of cataclysmic events, like the collision of neutron stars or the collapse of massive stars into black holes. Others suggest they could be linked to highly magnetized neutron stars, known as Magnetars, which occasionally release bursts of energy so powerful they can be detected across the universe. And then there's the more provocative idea: could FRBs be signals from advanced extraterrestrial civilizations? While this remains a fringe hypothesis, it's a tantalizing possibility that underscores just how little we know about these cosmic enigmas. Recent discoveries have only deepened the mystery. In 2020, astronomers detected the first FRB originating from within our own galaxy, linked to a magnetar. This breakthrough provided a crucial clue, suggesting that at least some FRBs are tied to these highly magnetic stellar remnants, but not all FRBs fit this pattern. Some repeat sporadically, while others are one-off events, hinting that multiple mechanisms might be at play. The race to pinpoint their sources has led to the development of cutting-edge telescopes and detection networks, like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which has become a key player in the hunt for these elusive signals. What's truly remarkable is how much we've learned in such a short time. FRBs aren't just cosmic curiosities, they're also tools for probing the universe. As these bursts travel across vast distances, they interact with the intergalactic medium, the sparse gas and dust between galaxies. By analyzing how FRB signals are distorted, scientists can map the distribution of matter in the cosmos, shedding light on the universe's large-scale structure. It's like using a flashlight to see through fog, revealing details we'd otherwise never detect. Yet, for all we've uncovered, FRBs remain one of the universe's most tantalizing mysteries. Each new detection brings us closer to understanding their origins, but also raises new questions. What triggers these bursts? Why do some repeat while others don't? And could they hold clues to phenomena we've yet to imagine? As we continue to unravel the secrets of FRBs, they remind us that the cosmos is full of surprises waiting to be discovered. And speaking of cosmic surprises, our next wonder takes us to a structure so vast, it challenges our understanding of the universe itself. A network of galaxies and dark matter that stretches across billions of light years. But that's a discovery for the next chapter in our journey through the cosmos. Stretching across the universe like an intricate spider's web, the cosmic web is one of the most awe-inspiring structures in existence. Imagine a vast network of glowing filaments, each one made up of dark matter and gas, weaving through the cosmos and connecting galaxies like beads on a string. This colossal framework isn't just a random arrangement, it's the backbone of the universe, the blueprint upon which everything is built. Without it, the galaxies we see scattered across the night sky wouldn't exist as we know them. The story of the cosmic web begins in the aftermath of the Big Bang. In those early moments, tiny fluctuations in density created ripples in the fabric of space-time. Over billions of years, gravity amplified these ripples, pulling matter together into dense nodes and stretching it into long, thread-like filaments. These filaments form the highways of the universe, guiding the flow of gas and dust into regions where galaxies and galaxy clusters form. It's a cosmic dance choreographed by gravity that shapes the very structure of the cosmos. What makes the cosmic web so fascinating is its sheer scale. These filaments stretch across hundreds of millions of light years, creating a sprawling network that links galaxies across unimaginable distances. And while we can't see the dark matter that forms the web's framework, its influence is undeniable. By mapping the distribution of galaxies and studying the light from distant quasars, astronomers have been able to trace the outlines of this invisible network, revealing a universe far more interconnected than we ever imagined. But the cosmic web isn't just a static structure, it's a dynamic, evolving system. Gas flows along these filaments, feeding the growth of galaxies and galaxy clusters. In some regions, filaments intersect, creating dense knots where clusters of galaxies form. In others, they stretch into the void, leaving vast, empty spaces known as cosmic voids. This interplay of structure and emptiness is what gives the universe its unique texture, a delicate balance between order and chaos. The cosmic web also plays a crucial role in the universe's evolution. By channeling matter into galaxies, it drives the formation of stars and planets, setting the stage for the emergence of life. Without this intricate network, the universe would be a very different place, a scattered, formless expanse rather than the vibrant, structured cosmos we see today. It's a reminder that even on the grandest scales, the universe is governed by patterns and processes that shape everything from the smallest atom to the largest galaxy. Yet, for all we've learned about the cosmic web, there's still much we don't understand. What exactly drives the flow of gas along these filaments? How do they influence the formation of supermassive black holes at the centers of galaxies? And what role do they play in the mysterious process of cosmic reionization, which transformed the early universe? These questions push the boundaries of our knowledge, challenging us to explore deeper into the fabric of the cosmos. As we unravel the secrets of the cosmic web, we're also led to confront a phenomenon that challenges our very understanding of matter itself, a force so elusive it's reshaping our view of the universe. But that's a story for the next wonder in our cosmic journey. At the heart of the universe lies a substance so rare, so enigmatic, that it seems almost otherworldly: antimatter. Picture this: every particle of matter we know, from the electrons in your phone to the stars in the night sky, has a mirror image, an exact opposite. This is antimatter, the cosmic counterpart to ordinary matter. But here's the catch: when matter and antimatter meet, they annihilate each other in a burst of pure energy. It's like a cosmic game of opposites where one cancels out the other, leaving behind nothing but light and radiation. What makes antimatter so fascinating is its scarcity. In the grand scheme of the universe, matter dominates while antimatter is vanishingly rare. Why this imbalance exists is one of the greatest unsolved mysteries in physics. According to the Big Bang theory, equal amounts of matter and antimatter should have been created in the early universe, yet somehow matter prevailed. Where did all the antimatter go? This question has puzzled scientists for decades, and the answer could reshape our understanding of the cosmos. Despite its rarity, antimatter isn't just a theoretical curiosity, it's real, and we've even managed to create it. At CERN, the European Organization for Nuclear Research, physicists use powerful particle accelerators to produce tiny amounts of antimatter. By smashing particles together at near light speeds, they can create antiprotons and positrons, the antimatter versions of protons and electrons. These particles are then trapped using magnetic fields, allowing scientists to study their properties in unprecedented detail. It's a delicate process requiring extreme precision, as even the slightest contact with ordinary matter would result in annihilation. The potential applications of antimatter are as breathtaking as they are futuristic. Because of its immense energy density, antimatter has been proposed as a potential fuel source for interstellar travel. Just 1 gram of antimatter could release as much energy as a nuclear bomb, a concept that sounds like science fiction but is grounded in real physics. However, the challenges are enormous. Producing even a fraction of a gram of antimatter would require vast amounts of energy and resources, making it impractical with current technology. Still, the idea of harnessing antimatter for energy remains a tantalizing possibility, one that could revolutionize space exploration. But antimatter isn't just about energy, it's also a key to unlocking the secrets of the universe. By studying how antimatter behaves, scientists hope to uncover why there's such a stark imbalance between matter and antimatter in the cosmos. Experiments at CERN, like ALPHA and ATRAP, are probing the properties of antimatter atoms, searching for even the tiniest differences between them and their matter counterparts. These differences, no matter how small, could hold the key to understanding why the universe is made of matter and not antimatter. As we delve deeper into the mysteries of antimatter, we're reminded that the universe is full of surprises. From its creation in the fiery aftermath of the Big Bang to its potential as a future energy source, antimatter challenges our understanding of the cosmos at every turn. And just when you think the universe couldn't get any more mysterious, there's another phenomenon waiting to be discovered, one that defies the very laws of physics as we know them. But that's a story for the next wonder in our cosmic journey. Deep within the cosmos, there are explosions so colossal, so unimaginably bright, they outshine entire galaxies, even if only for a few fleeting seconds. These are gamma-ray bursts, or GRB, the most luminous events in the universe. Picture a cosmic fireworks display, but on a scale so immense that it defies comprehension. These bursts release more energy in a matter of seconds than our Sun will emit over its entire 10 billion-year lifetime, yet their brilliance comes with a deadly edge. If a gamma-ray burst were to occur within a few thousand light-years of Earth, the intense radiation could strip away our ozone layer, leaving the planet vulnerable to the sun's ultraviolet rays. It's a sobering reminder of how fragile life can be in the face of the universe's raw power. Gamma-ray bursts are born from some of the most violent events in the cosmos. One type, known as a long gamma-ray burst, occurs when a massive star exhausts its fuel and collapses under its own gravity, triggering a supernova and giving birth to a black hole. The explosion sends jets of energy shooting outward at nearly the speed of light, creating a burst so intense it can be detected across the universe. Another type, short gamma-ray bursts, are thought to result from the merger of two neutron stars. When these ultra-dense objects collide, they unleash a torrent of energy, producing a burst that lasts just milliseconds but leaves an indelible mark on the cosmos. What makes gamma-ray bursts so remarkable isn't just their power, it's what they can teach us about the universe. Because these bursts are so bright, they act as cosmic beacons, illuminating the distant reaches of space. By studying their light, astronomers can peer back in time to the early universe, observing conditions that existed just a few 100 million years after the Big Bang. It's like having a time machine that allows us to witness the birth of the first stars and galaxies, offering clues about how the cosmos evolved into the vast, intricate web we see today. But gamma-ray bursts aren't just tools for studying the past, they also help us understand the present. The explosions produce gravitational waves, ripples in space-time that carry information about their origins. By combining observations of light and gravitational waves, scientists can piece together the story of these cataclysmic events, unraveling the physics that drives them. It's a field of study that's still in its infancy, but one that holds immense promise for unlocking the secrets of the universe. And while gamma-ray bursts are some of the most energetic phenomena in the cosmos, they're not the only ones that leave an impact. Beyond these brilliant explosions lies another cosmic mystery, one that doesn't just light up the universe, but also fills it with eerie, otherworldly sounds. But that's a discovery for the next chapter in our journey through the cosmos. Among the many cosmic marvels, pulsars stand out as some of the most rhythmic and precise objects in the universe. These rapidly spinning neutron stars emit beams of radio waves that sweep across space like the steady pulse of a cosmic metronome. But what's truly remarkable is that these radio waves can be converted into sound, a haunting, otherworldly hum that echoes through the cosmos. Imagine a heartbeat, but one that beats thousands of times per second. Its rhythm so precise it rivals the accuracy of atomic clocks. These are the sounds of pulsars, a cosmic symphony that has captivated astronomers and inspired imaginations for decades. The discovery of pulsars in 1967 was nothing short of revolutionary. At first, the regular pulses of radio waves baffled scientists who jokingly nicknamed the signal LGM-1 for little green men, as they wondered if it could be a message from an alien civilization. But the truth was even more extraordinary. The signals were coming from a rapidly spinning neutron star, a remnant of a supernova explosion so dense that a teaspoon of its material would weigh billions of tons. As these neutron stars spin, their powerful magnetic fields funnel beams of radiation into space. When these beams sweep past Earth, we detect them as rhythmic pulses, a cosmic lighthouse blinking in the void. What makes pulsars so fascinating isn't just their rhythm, but their incredible utility. Their precise pulses have been used as natural navigational tools, helping spacecraft orient themselves in the vastness of space. By comparing the timing of pulses from multiple pulsars, scientists can triangulate a spacecraft's position with astonishing accuracy, a technique known as pulsar navigation. It's like using the stars as a cosmic GPS, but instead of satellites, the beacons are remnants of dead stars scattered across the galaxy. Pulsars also serve as extraordinary laboratories for testing the laws of physics. Their strong gravitational fields and rapid spins make them ideal for probing Einstein's theory of general relativity. For example, the first binary pulsar system discovered in 1974 allowed scientists to observe the effects of gravitational waves indirectly, decades before they were directly detected. The precise timing of pulsar pulses has even been used to study the behavior of spacetime itself, confirming predictions made by Einstein over a century ago. But pulsars aren't just tools for science, they're also potential guides for future interstellar travel. Some scientists have proposed using pulsars as natural lighthouses, their steady pulses providing a reliable roadmap for navigating the galaxy. Imagine a future where spacecraft use the rhythmic hum of pulsars to chart their course through the stars, their beams cutting through the darkness like cosmic signposts. It's a vision that blends the practical with the poetic, a reminder that the universe itself might hold the keys to our exploration of the unknown. As we listen to the hum of pulsars, we're reminded that the cosmos is not just a place of silence and emptiness, but one filled with rhythm and sound. These cosmic heartbeats connect us to the universe in ways that are both profound and practical, offering a glimpse into the intricate dance of matter, energy, and time. And as we tune into these celestial rhythms, another mystery awaits, one that hints at the existence of dimensions beyond our own, a phenomenon that could reshape our understanding of reality itself. Imagine the universe as a vast, tranquil pond. Now, picture dropping a stone into its center, ripples spread outward, distorting the surface in every direction. This is the essence of gravitational waves, ripples in the very fabric of space-time itself. But unlike the gentle ripples on a pond, these waves are born from the most violent events in the cosmos, colliding black holes, merging neutron stars, and even the explosive deaths of massive stars. In 2015, humanity achieved a monumental breakthrough, the first direct detection of gravitational waves. This discovery wasn't just a scientific triumph, it was the opening of a new window into the universe, one that allows us to hear the cosmos in ways we never could before. The story of gravitational waves begins with Albert Einstein. Over a century ago, his theory of general relativity predicted that massive objects like black holes or neutron stars could warp space-time, creating ripples that travel at the speed of light. For decades, these waves remained elusive, hidden from our instruments by their faintness and the immense distances they traveled. But on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. The observatory detected a signal, a faint chirp lasting just a fraction of a second, that originated from the collision of two black holes over 1 billion light-years away. It was a moment of profound significance, confirming Einstein's predictions and marking the dawn of a new era in astronomy. What makes gravitational waves so revolutionary is their ability to reveal cosmic events that are invisible to traditional telescopes. Unlike light, which can be blocked or distorted by dust and gas, gravitational waves pass through everything, carrying information about their origins directly to us. They've already provided insights into the nature of black holes, the properties of neutron stars, and even the expansion rate of the universe. Each detection is like tuning into a cosmic symphony, where each wave tells a story about the forces that shaped it. The potential of gravitational wave astronomy is staggering. With each new detection, scientists are uncovering hidden phenomena, events so extreme they push the boundaries of our understanding. For example, the merger of two neutron stars in 2017 not only produced gravitational waves but also a burst of light across multiple wavelengths, from gamma rays to radio waves. This multi-messenger observation provided a wealth of data, from the creation of heavy elements like gold and platinum to insights into the behavior of matter under extreme conditions. It was a cosmic Rosetta Stone decoding the universe's most violent and mysterious processes. But the journey is far from over. New observatories like the upcoming LISA mission aim to detect gravitational waves from supermassive black holes and other massive objects. These future detections could reveal even more about the universe's structure, from the formation of galaxies to the nature of dark energy. Gravitational waves are more than just ripples in space-time. They're a new language, allowing us to listen to the whispers of the cosmos and uncover its deepest secrets. As we continue to explore this new frontier, another celestial mystery awaits, one that defies classification and challenges our very understanding of what's possible in the universe. But that's a discovery for the next chapter in our cosmic journey. Imagine a planet drifting alone in the vast emptiness of space, untethered to any star, wandering the galaxy in perpetual darkness. These are rogue planets, worlds that orbit no sun, their surfaces bathed in eternal night. Unlike the familiar planets in our solar system, these free-floating wanderers are not bound by the gravitational pull of a star. Instead, they roam the cosmos like cosmic nomads, untethered and untraceable, challenging everything we thought we knew about how planets form and exist. Rogue planets are born in the chaos of stellar nurseries, regions of space where stars and planets form from swirling clouds of gas and dust. Most planets, like those in our solar system, remain gravitationally bound to their parent stars. But rogue planets are the exceptions, cast adrift by violent interactions with other celestial bodies or ejected from their nascent systems entirely. Some may even form directly from collapsing gas clouds, never having orbited a star at all. The result is a population of planets that wander the galaxy in isolation, their surfaces frozen and dark, yet potentially teeming with secrets. What's truly fascinating about rogue planets is their potential to harbor life. It's a concept that seems almost paradoxical, a world without a star, where the sun never rises and the sky is forever black. Yet, beneath their icy surfaces, some rogue planets could possess subsurface oceans, kept liquid by the heat generated from radioactive decay or tidal forces. These hidden oceans might provide the perfect conditions for life to emerge, shielded from the harsh radiation of space and the extremes of temperature. It's a tantalizing possibility that redefines our search for life beyond Earth, expanding the boundaries of what we consider habitable. Detecting these elusive worlds, however, is no easy task. Without the light of a star to illuminate them, rogue planets are nearly invisible to traditional telescopes, but astronomers have developed ingenious methods to hunt for them. One technique relies on gravitational microlensing, where the gravity of a rogue planet bends and magnifies the light of a distant star as it passes in front of it. This fleeting event can reveal the presence of a rogue planet, even if it's light years away. Another approach involves searching for the faint heat signatures these planets emit, remnants of their formation or internal processes. Each discovery of a rogue planet adds another piece to the puzzle of planetary formation and evolution. These lonely worlds remind us that the universe is full of surprises, and that the rules we've established for how planets behave might only scratch the surface of what's possible. They challenge us to rethink our assumptions about the cosmos, pushing the boundaries of our imagination and our science. And just when you think the universe couldn't get any more mysterious, there's a phenomenon that blurs the line between science and science fiction, a cosmic enigma that defies explanation and sparks the imagination. But that's a story for the next wonder in our cosmic journey. Picture a shortcut through the fabric of the universe, a tunnel that bends space and time, connecting two distant points in an instant. These hypothetical passages are known as wormholes, and they're one of the most tantalizing concepts in theoretical physics. Rooted in the equations of Einstein's theory of general relativity, wormholes are bridges that could, in theory, link far-flung regions of the cosmos, potentially allowing travel across vast distances without the constraints of speed or time. But are they just a mathematical curiosity, or could they exist in the real universe? The answer lies at the intersection of science and imagination. The idea of wormholes stems from Einstein's equations, which describe how massive objects warp the fabric of space-time. In theory, a wormhole would consist of two mouths connected by a throat, forming a tunnel through which matter or even light could travel. One of the most fascinating aspects of wormholes is their potential for faster-than-light travel. While nothing can move through space faster than light, a wormhole could allow a spacecraft to bypass the vast distances between stars and galaxies, effectively arriving at its destination faster than light would in a straight line. It's like folding a piece of paper so that 2 points touch, creating a shortcut through the void. But here's the catch: wormholes, as predicted by theory, are incredibly unstable. The moment one forms, it would likely collapse under its own gravity unless held open by some form of exotic matter with negative energy, a substance that has never been observed in nature. Without this stabilizing force, the wormhole would snap shut, trapping anything inside. Even if we could create or find a stable wormhole, traversing it would come with its own set of challenges. The intense gravitational forces at its core could tear apart anything that entered, and the journey might involve unpredictable distortions of time and space. It's a cosmic gamble, one that raises as many questions as it answers. Despite these challenges, wormholes remain a captivating subject for scientists and science fiction writers alike. They offer a glimpse into the possibilities of interstellar travel and the profound ways in which the universe might be connected. Some theories even suggest that wormholes could be gateways to other universes or different points in time, opening up the tantalizing possibility of time travel. While these ideas remain speculative, they push the boundaries of our understanding, challenging us to rethink what's possible in the cosmos. As we ponder the mysteries of wormholes, another celestial phenomenon beckons, one that emits light so strange it seems to defy explanation. This enigmatic object, shrouded in mystery, could hold clues to some of the universe's deepest secrets, but that's a discovery for the next chapter in our cosmic journey. Stretching across the cosmos like a colossal blank canvas, the Boötes Void is one of the most mysterious and unsettling regions in the universe. Known as the Great Nothing, this enormous expanse spans an astonishing 330 million light-years, a distance so vast it could contain thousands of galaxies. Yet, instead of glittering with starlight, it's eerily empty, a cosmic desert where galaxies are few and far between. To put its scale into perspective, if the Milky Way were placed in the center of the Boötes Void, our nearest galactic neighbor would be millions of light-years away. It's a place where the universe seems to hold its breath, a void so immense it challenges our understanding of how matter is distributed across space. The nickname, the Great Nothing, isn't just poetic, it's a literal description of its unsettling emptiness. While most regions of the universe are teeming with galaxies, the Boötes Void is home to only a handful, scattered like lonely islands in an endless sea. This stark contrast raises profound questions about the structure of the cosmos. How can such a vast region of space be so empty, and what does its existence tell us about the universe's origins and evolution? These questions have intrigued astronomers since the void's discovery in the 1980s, sparking a wave of research and speculation. One leading theory suggests that the Boötes Void might be the result of smaller voids merging over billions of years, creating a single, colossal emptiness. Another possibility is that it's a remnant of the early universe, a relic from a time when matter was distributed unevenly after the Big Bang. In this scenario, the void could be a cosmic fossil, preserving a snapshot of the universe's infancy. But perhaps the most intriguing idea is that it's evidence of something even more profound, a hint at the influence of dark energy, the mysterious force driving the universe's accelerating expansion. Could the Boötes Void be a signpost pointing us toward the unseen forces shaping the cosmos? Despite its emptiness, the Boötes Void isn't completely devoid of wonder. The few galaxies that do reside within it are fascinating in their own right, some of them among the oldest and most distant ever observed. Studying these galaxies offers a glimpse into the universe's past, revealing clues about how galaxies form and evolve in such extreme environments. Yet, even with these rare cosmic inhabitants, the void's overwhelming emptiness remains its defining feature, a haunting reminder of the universe's vastness and the mysteries that still lie beyond our grasp. As we ponder the enigma of the Boötes Void, it's hard not to feel a sense of awe at the scale and strangeness of the cosmos. This vast, empty region isn't just a curiosity, it's a window into the universe's grand design, a place where the rules we think we know are stretched to their limits. And just when you think the universe couldn't get any more mysterious, there's a phenomenon that reveals its violent, explosive past, one that reshapes entire galaxies and leaves behind echoes of chaos. But that's a story for the next wonder in our cosmic journey. Few events in the universe rival the sheer power and spectacle of a supernova, a cataclysmic explosion that marks the death of a massive star. Imagine a star millions of times larger than our Sun, reaching the end of its life. Its core collapses under its own gravity, triggering a shockwave so violent that it rips the star apart in a blinding flash of light. For a brief moment, a single supernova can outshine an entire galaxy, releasing more energy than our Sun will emit in its entire lifetime. But this isn't just a cosmic fireworks display, it's a transformative event, one that shapes the very fabric of the universe. At the heart of a supernova lies a profound cosmic alchemy. As the star's core collapses, temperatures and pressures reach unimaginable levels, fusing atoms together to create elements heavier than iron, gold, silver, uranium, and many others. These elements are then blasted into space, scattering across the cosmos like seeds on the wind. Over billions of years, they become the building blocks of new stars, planets, and even life itself. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the fiery hearts of exploding stars. In a very real sense, we are all made of stardust, the legacy of supernova that lit up the universe long before Earth existed. But supernova aren't just creators, they're also cosmic messengers. Because of their incredible brightness, they serve as standard candles, astronomical tools that help scientists measure vast distances across the universe. By comparing a supernova's apparent brightness to its known intrinsic brightness, astronomers can calculate how far away it is, mapping the expansion of the universe itself. It was through studying supernova, particularly a type known as Type Ia, that scientists discovered dark energy, the mysterious force driving the universe's accelerated expansion. These explosions, born from the death of stars, have become key to understanding the fate of the cosmos. Recent observations have only deepened our appreciation for these stellar explosions. In 2022, astronomers witnessed one of the closest supernova in decades, a dazzling event in the Pinwheel Galaxy that allowed them to study the explosion in unprecedented detail. From the shockwave's aftermath to the formation of heavy elements, each new observation adds another layer to our understanding of these cosmic powerhouses. And with advanced telescopes like the James Webb Space Telescope now online, the future of supernova research looks brighter than ever. Yet for all their brilliance, supernova are fleeting. Within weeks or months, their light fades, leaving behind a remnant, a neutron star, a black hole, or a glowing cloud of gas and dust. But even in their aftermath, they continue to shape the universe, seeding it with the elements needed for new stars, planets, and life. It's a cycle as old as the cosmos itself, a testament to the interconnectedness of all things. As we marvel at the explosive beauty of supernova, another celestial phenomenon awaits, one that harnesses energy on a scale even these stellar giants can't match. This cosmic powerhouse, shrouded in mystery, could hold the key to understanding some of the universe's most profound secrets. But that's a discovery for the next chapter in our cosmic journey. Among the universe's most extreme objects, magnetars stand out as cosmic powerhouses of unimaginable ferocity. These are neutron stars, the remnants of massive stars that have collapsed under their own gravity. But with a twist, they possess magnetic fields billions of times stronger than anything we've ever encountered on Earth. To put this into perspective, if a magnetar were located halfway between Earth and the Moon, its magnetic field would strip the information from every credit card on the planet. It's a force so intense it can distort the very structure of atoms, tearing them apart in a phenomenon known as spaghettification. Yet, this is just the beginning of what makes magnetars so extraordinary. Magnetars are born from the most violent events in the cosmos, supernova explosions that leave behind a dense, spinning core. As this core collapses, it amplifies the star's magnetic field to unimaginable levels, creating a magnetar. These objects are incredibly rare, with only a few dozen confirmed in our galaxy, but their impact is anything but subtle. Their magnetic fields are so powerful that they can trigger starquakes, massive tremors on the magnetar's surface that release energy equivalent to billions of nuclear bombs. These quakes ripple through space, producing bursts of gamma rays and X-rays that can be detected across the universe. One of the most dramatic events associated with magnetars is the gamma ray flare. In just a fraction of a second, a magnetar can release more energy than the Sun emits in 100,000 years. These flares are so intense that they can be detected billions of light years away, lighting up the cosmos like a cosmic flashbulb. In 2004, a magnetar in our own galaxy unleashed a flare so powerful that it briefly outshone the full moon, even though it was located 50,000 light years away. If such a flare occurred closer to Earth within just a few thousand light years, it could strip away our ozone layer, leaving the planet vulnerable to harmful solar radiation. It's a sobering reminder of the raw power these objects wield. Despite their destructive potential, magnetars are also windows into some of the most extreme physics in the universe. Their intense magnetic fields and rapid spins make them natural laboratories for studying matter under conditions that can't be replicated on Earth. For example, their surfaces are thought to be composed of a bizarre state of matter known as a nuclear pasta, where protons and neutrons are crushed into shapes resembling spaghetti or lasagna sheets. These strange structures are a testament to the extreme pressures and densities found in magnetars, offering clues about the behavior of matter at its limits. Yet, for all we've learned about magnetars, they remain shrouded in mystery. How do their magnetic fields become so strong? What triggers their violent outbursts? And what happens when two magnetars collide? These questions push the boundaries of our understanding, challenging us to explore the extremes of the cosmos. As we delve deeper into the secrets of magnetars, we're also led to consider a phenomenon that reveals the universe's hidden symmetries, a cosmic mystery that ties together the forces of nature in ways we're only beginning to understand. Step into the earliest moments of the universe, and you'll find a faint echo of its birth, a whisper of light that has traveled across billions of years to reach us. This is the cosmic microwave background, or CMB, the afterglow of the Big Bang. Imagine it as a cosmic photograph, a snapshot of the universe when it was just 380,000 years old. At that time, the cosmos was a seething, opaque soup of particles and radiation. But as the universe expanded and cooled, protons and electrons combined to form neutral atoms, allowing light to travel freely for the first time. This light, stretched and cooled by the expansion of space over billions of years, is what we now detect as the CMB, a faint glow that permeates every corner of the universe. The discovery of the CMB in 1965 was a watershed moment in cosmology. Two astronomers, Arno Penzias and Robert Wilson, stumbled upon this faint radiation while testing a sensitive radio antenna. At first, they thought it was noise, a persistent hiss they couldn't eliminate, no matter how much they cleaned their equipment. But this noise turned out to be the oldest light in the universe, a direct remnant of the Big Bang. It was a discovery so profound that it earned them the Nobel Prize and solidified the Big Bang theory as the cornerstone of modern cosmology. What makes the CMB so remarkable is its uniformity. No matter where we look in the sky, this faint glow is almost the same temperature, about 2.7 degrees above absolute zero. But within this uniformity, there are tiny fluctuations or anisotropies, regions where the temperature varies by just a fraction of a degree. These fluctuations are like cosmic fingerprints, revealing the seeds of structure in the early universe. From these tiny ripples, gravity pulled matter together over billions of years, forming galaxies, stars, and planets. In a very real sense, the CMB is the blueprint of the cosmos, a map that traces the origins of everything we see today. The anisotropies in the CMB also hold clues to some of the universe's deepest mysteries. For instance, they provide evidence for dark matter and dark energy, the invisible forces that shape the cosmos. The patterns in the CMB suggest that dark matter, which doesn't interact with light, played a crucial role in pulling matter together, while dark energy is driving the universe's accelerated expansion. It's a testament to how much we can learn from this ancient light, a cosmic time capsule that continues to reveal new insights about the universe's past, present, and future. As we study the CMB, we're reminded of how interconnected the universe truly is. This faint glow isn't just a relic of the past, it's a living record, a testament to the universe's dynamic history. And just when you think the cosmos couldn't get any more mysterious, there's a celestial object that challenges our understanding of time itself, a phenomenon so strange it bends the very fabric of reality. But that's a discovery for the next chapter in our cosmic journey. While black holes have long captivated our imaginations as cosmic vacuum cleaners, what if there were objects that did the exact opposite? Enter white holes, theoretical counterparts to black holes that defy everything we know about how gravity works. Imagine a cosmic fountain, endlessly spewing matter and energy into the universe instead of devouring it. These enigmatic objects, rooted in the equations of Einstein's general relativity, are the polar opposites of black holes, yet they remain firmly in the realm of theory. While no white hole has ever been observed, their existence would rewrite the rules of the cosmos, offering a glimpse into the universe's most profound symmetries. The concept of white holes arises from the same math that describes black holes. In Einstein's equations, the solutions that predict black holes can also be reversed, suggesting the possibility of objects that expel matter and energy rather than trapping them. If a black hole is a one-way street into oblivion, a white hole is a cosmic exit door, ejecting everything that enters it back into the universe. Some scientists speculate that white holes could even be connected to black holes through wormholes, forming a bridge between two distant regions of space-time. It's a tantalizing idea. Black holes swallow matter, and white holes spit it out, creating a cosmic cycle of destruction and creation. But here's the catch: white holes are incredibly unstable. Unlike black holes, which form naturally from the collapse of massive stars, white holes would require a very specific set of conditions to exist. In fact, many physicists argue that white holes are purely mathematical curiosities with no real-world counterpart. Yet their potential implications are too intriguing to ignore. If white holes do exist, they could help explain some of the universe's most puzzling phenomena, from the origins of gamma-ray bursts to the mysterious behavior of dark energy. They might even offer a way to reconcile the laws of quantum mechanics with general relativity, two frameworks that have long resisted unification. One particularly fascinating idea is that white holes could be the other side of black holes. In this scenario, matter that falls into a black hole might re-emerge from a white hole in a different part of the universe, or even in a different universe altogether. This concept ties into the idea of wormholes, theoretical tunnels through space-time that could connect distant regions or even different dimensions. While these ideas remain speculative, they push the boundaries of our understanding, challenging us to think beyond the confines of our current knowledge. As we explore the mysteries of white holes, we're reminded that the universe is full of symmetries and opposites, from matter and antimatter to black holes and their hypothetical counterparts. These cosmic dualities hint at a deeper order underlying the chaos of the cosmos, a hidden beauty waiting to be uncovered. And just when you think the universe couldn't get any more enigmatic, there's a phenomenon that reveals its most dazzling display of light, a celestial spectacle so breathtaking it's like nature's own masterpiece. But that's a story for the next chapter in our cosmic journey. Rising like cosmic cathedrals in the heart of the Eagle Nebula, the Pillars of Creation stand as one of the most iconic and awe-inspiring sights in the universe. These towering columns of gas and dust, captured in stunning detail by the Hubble Space Telescope, are more than just a breathtaking spectacle. They're a stellar nursery, a place where new stars are born. Each pillar, stretching light years into the void, is a crucible of creation where the raw materials of the cosmos come together to ignite the fires of young stars. It's a scene that feels almost sacred, a reminder of the universe's endless capacity for renewal and transformation. What makes the Pillars of Creation so remarkable is their role in the process of star formation. Within these colossal structures, dense pockets of gas and dust collapse under their own gravity, heating up until nuclear fusion ignites, giving birth to new stars. The Hubble images reveal intricate details, tendrils of gas illuminated by the intense radiation of nearby stars, glowing like embers in a cosmic forge. These newborn stars, still shrouded in their dusty cocoons, emit powerful winds and radiation that sculpt the surrounding gas into the ethereal shapes we see. It's a delicate balance where the forces of creation and destruction dance in harmony, shaping the future of the nebula. But the Pillars of Creation are more than just a snapshot of star birth. They're also a window into the past. The light we see from these structures has traveled 7,000 years to reach us, meaning we're witnessing them as they appeared long before human civilization began. Yet, even as we marvel at their beauty, we know their fate is sealed. A nearby supernova, whose shockwave has already reached the pillars, will eventually tear them apart, scattering their gas and dust across the cosmos. It's a poignant reminder that even the most majestic structures in the universe are transient, subject to the relentless forces of time and change. The Hubble images of the Pillars of Creation have become iconic, not just for their beauty but for what they represent, a moment of cosmic artistry frozen in time. They've inspired countless people, from professional astronomers to casual stargazers, to ponder the mysteries of star formation and the cycles of life and death that govern the universe. Yet, even as we celebrate their splendor, they also challenge us to think about the fragility of existence and the impermanence of all things. As we reflect on the fleeting majesty of the Pillars of Creation, another celestial wonder beckons, one that blurs the line between the familiar and the alien, raising profound questions about the nature of life itself. This enigmatic object, shrouded in mystery, could hold the key to understanding whether life exists beyond our own world, and that's a discovery that could change everything. Beyond the familiar planets of our solar system lies a realm of worlds so distant, they were once thought to exist only in science fiction. These are exoplanets, planets orbiting stars other than our Sun. Among them, a rare few lie within what astronomers call the habitable zone, the sweet spot where temperatures might allow liquid water to exist, and where there's water, there's the tantalizing possibility of life. These distant worlds, some eerily similar to Earth, challenge our understanding of what it means to be habitable and ignite our curiosity about whether we're truly alone in the universe. One of the most exciting discoveries in this cosmic hunt is Proxima Centauri b, a planet orbiting the closest star to our solar system, just over 4 light-years away. This rocky world, roughly the size of Earth, sits comfortably within its star's habitable zone. But here's the twist: Proxima Centauri is a red dwarf, a star much cooler and dimmer than our Sun. This means the planet is likely tidally locked, with one side perpetually facing the star and the other shrouded in eternal darkness. Could life exist in such extreme conditions? Scientists speculate that a thick atmosphere or vast oceans might distribute heat, creating pockets where life could thrive. It's a tantalizing thought, a world so close, yet so alien, that it forces us to rethink the boundaries of habitability. Then there's TRAPPIST-1e, part of a remarkable system of 7 Earth-sized planets orbiting another red dwarf star. Located about 40 light-years away, this planet has captured the imagination of astronomers and science enthusiasts alike. What makes TRAPPIST-1e so intriguing is its potential for liquid water. Its size, mass, and distance from its star suggest it could have a rocky surface and a stable atmosphere, ingredients that make it one of the most promising candidates for life beyond Earth. But the TRAPPIST-1 system isn't just about one planet. It's a cosmic laboratory, offering a glimpse into how multiple Earth-like worlds can coexist around a single star. Finding these distant worlds is no small feat. Astronomers use a variety of ingenious methods to detect exoplanets, from measuring the slight dimming of a star as a planet passes in front of it, a technique called the transit method, to detecting the tiny wobble a planet's gravity induces in its host star, known as the radial velocity method. Each discovery adds to our growing catalog of exoplanets, now numbering in the thousands, and each one brings us closer to answering the ultimate question: are we alone? The implications of these discoveries are profound. If life exists on even one of these distant worlds, it would transform our understanding of biology, chemistry, and the universe itself. It would mean that life isn't a rare fluke confined to Earth, but a cosmic phenomenon woven into the fabric of the universe. And as we continue to explore these distant worlds, we're also led to consider a phenomenon that reveals the universe's ultimate fate, a force so powerful it's shaping the destiny of everything we see. But that's a story for the final chapter in our cosmic journey. As we've journeyed through the cosmos, marveling at its wonders, there's one inevitability we must confront, a fate so profound, it redefines our understanding of time, energy, and existence itself. This is the heat death of the universe, a theory that paints a hauntingly beautiful picture of the cosmos' ultimate end. Imagine a universe where every star has burned out, every galaxy has faded into darkness, and every form of energy has been evenly distributed, leaving no room for change or motion. It's a state of maximum entropy, where the universe reaches a cold, silent equilibrium, a cosmic stillness that marks the end of all activity. The concept of heat death stems from the second law of thermodynamics, which states that in an isolated system, entropy, or disorder, always increases over time. In simpler terms, energy tends to spread out evenly, like heat dissipating into a cold room. Apply this principle to the universe, and you see a future where all stars exhaust their fuel. Black holes evaporate through Hawking radiation, and even the last remnants of matter decay into radiation. What remains is a vast, uniform expanse of energy, so evenly distributed that no work can be done. No stars will ignite, no planets will form, and no life will emerge. It's a universe that has run its course, a cosmic clock that has finally stopped ticking. Yet there's a strange beauty in this vision of the universe's end. It's a reminder of the delicate balance that allows life and complexity to exist in the first place. The very processes that drive the universe toward heat death, the fusion of stars, the collapse of matter, the flow of energy are the same processes that created the conditions for life. In a way, the universe's end is a testament to its beginning, a final chapter that echoes the Big Bang in its quiet, inevitable symmetry. It's a cycle as old as time itself, from the fiery birth of the cosmos to its cold, silent conclusion. The implications of this theory are both humbling and profound. If the heat death is indeed the universe's fate, it forces us to confront the impermanence of everything we know. Galaxies, stars, planets, and even the atoms that make up our bodies are fleeting in the grand scheme of cosmic time. Yet, this impermanence also underscores the preciousness of the here and now. The universe, for all its vastness, has given us a brief window of opportunity, a chance to explore, to wonder, and to create meaning in an otherwise indifferent cosmos. As we reflect on this ultimate fate, it's worth pausing to consider the journey we've taken through these 22 wonders. From the gravitational pull of the Great Attractor to the ethereal glow of the cosmic microwave background, each marvel has revealed a new facet of the universe's complexity and beauty. We've explored the birth of stars, the collision of black holes, and the possibility of life on distant worlds. We've marveled at the intricate dance of matter and energy, and we've glimpsed the profound mysteries that still lie beyond our understanding. The heat death of the universe is not just a scientific theory, it's a story about the cosmos itself, a narrative that connects every wonder we've encountered. It's a reminder that the universe is not static but dynamic, a tapestry of forces and phenomena that shape its past, present, and future. And while the idea of an end may seem bleak, it also invites us to appreciate the extraordinary journey that brought us here, to this moment of discovery and wonder. The universe may one day grow cold and still, but for now, it's alive with possibilities, waiting for us to explore its endless mysteries. As we reach the end of our journey through the cosmos, it's time to pause and reflect on the 22 hidden wonders we've explored, each one a testament to the universe's boundless creativity and mystery. From the gravitational pull of the Great Attractor to the ethereal glow of the cosmic microwave background, these phenomena remind us that the universe is far stranger and more beautiful than we could ever imagine. They challenge our understanding, spark our curiosity, and invite us to look beyond the familiar into the vast, uncharted realms of existence. These wonders aren't just scientific curiosities, they're stories. Stories of creation and destruction, of forces so immense they shape galaxies and particles so elusive they redefine reality. They show us that the universe is a place of infinite complexity, where the laws of physics bend and twist in ways that defy our everyday experience. From the birth of stars in the pillars of creation to the explosive power of gamma-ray bursts, each marvel reveals a new layer of the cosmos, inviting us to ask deeper questions and seek greater understanding. But these wonders do more than expand our knowledge, they also connect us. They remind us that we're part of something much larger, a cosmic tapestry woven from the same threads that form stars, planets, and galaxies. When we gaze at the night sky, we're not just observers, we're participants in a story that began billions of years ago and will continue long after we're gone. It's a humbling thought, but also an empowering one. The universe is ours to explore, to question, and to marvel at. So where do we go from here? The journey doesn't end with this video. The cosmos is vast and its mysteries are endless. Whether you're stargazing from your backyard, diving into the latest scientific discoveries, or simply letting your imagination wander among the stars, there's always more to discover. Every new observation, every breakthrough brings us closer to understanding the universe and our place within it. As the astronomer Carl Sagan once said, "Somewhere, something incredible is waiting to be known." Let these words guide you as you continue to explore the wonders of the cosmos. Share your thoughts in the comments below. What hidden wonder captivated you the most? And if you're hungry for more cosmic adventures, don't forget to subscribe and join us as we delve deeper into the mysteries of the universe. The stars are calling, and the journey is just beginning.